Welcome back to the Deep Dive, your shortcut to being well-informed. Have you ever stopped to think about those invisible safety nets? The ones keeping our digital world from, well, completely falling apart.
Hmm. It's something we often take for granted.
Exactly. Imagine a really crucial system inside a huge company. You know, the kind processing every single financial transaction or managing every customer order, maybe tracking every single item moving around the globe.
Yeah, the absolute core of the business operations.
Right. So what happens if that system just goes dark suddenly?
Chaos. Pure chaos, usually.
You can just picture it, can't you? The lost revenue stacking up, the sheer paralysis spreading through the entire business.
It's a scenario companies spend a lot of effort trying to avoid.
Well, today we're pulling back the curtain on a specific technology designed to prevent exactly that nightmare.
Yeah.
SAP HANA High Availability and Replication.
A really fundamental piece of the puzzle for enterprise resilience.
We've spent time poring over a stack of really fascinating source material. It walks us through the nuts and bolts, you know, how businesses make sure their critical data is always available, always online.
Mm-hmm.
Our mission today is to help you understand the, frankly, incredible engineering behind keeping these vast amounts of data accessible, even when, you know, disaster strikes.
It's definitely more than just a technical setting. It's really become a strategic imperative, especially in today's always-on economy.
Just a journey, then.
Yeah, you could say that. A journey into the heart of data resilience. We're not just exploring what these systems are at a basic level, but digging into why they're absolutely essential for any modern enterprise.
Okay.
We'll unpack the practical steps, the how-to. We'll look at the underlying architectural ideas, and even touch on some of the common, often quite tricky challenges that pop up when you try to set up such a robust system.
The real-world stuff.
Exactly. It's all about building genuine trust in your data infrastructure, knowing it won't let you down.
Okay, so let's start right at the beginning, the fundamental question. In an ideal world, why would any company actually need something as complex, as seemingly intricate, as high availability for a database like SAP HR?
Right.
What's the real-world impact if it's not there? If you just, rely on that single system?
You've basically hit on the critical vulnerability right there. Imagine a business could be a global retailer, a major bank, doesn't matter, relying solely on just one SAP agent database instance.
Okay, one single database.
Yes, and this single instance processes everything, their finance, sales, logistics, everything. Now think about what happens if that single Asia node has any kind of issue.
Any kind.
Literally any kind. It could be something almost mundane like a routine operating system update that just goes wrong. Maybe it leaves the system unable to boot.
Oh, okay.
Or maybe it's a more dramatic sudden OS failure. Could be a physical hardware component just giving up a memory stick failing. Maybe a disk controller stops responding.
Hardware failures happen.
They do. And even seemingly minor internal issues like the, database host simply running out of disk space.
Oh, yeah.
Or a severe memory problem within the database software itself. Any one of these things can bring that single system to its knees.
And they all lead to the same outcome?
Essentially, yes. They all represent what we call a single point of failure for the entire SAP application ecosystem that relies on that database.
And when you say single point of failure, what does that actually translate to for the business day-to-day? What are the immediate and maybe the knock-on effects if that one system goes down?
Well, the consequences aren't just immediate. They're often really severe and can spread quite far.
Okay.
If that single solitary HANA database goes offline, the entire SAP application connected to it, which, let's be clear, is often the digital backbone of the company, goes down with it.
The whole thing.
The whole thing. This means a complete instant halt to operations. Employees across every department suddenly lose the ability to do their jobs. Customer service reps, they can't access client records.
Right.
Sales teams can't create new orders. Finance departments, they can't process transactions, can't run those critical month-end reports. Supply chain logistics just stop, dead in the water.
Wow. It really paints a picture.
Think about it. Almost every employee, every business process, every key decision might rely on data coming out of SAP for their daily tasks. If the underlying AI database isn't available, the entire business essentially grinds to a halt. Our source material really emphasizes this direct one-to-one dependency. AA down means SAP is down, period.
So it's not just like an inconvenience.
Oh, far from it. For a medium to large enterprise, we're talking potentially millions in lost revenue for every hour the system is offline.
Millions per hour.
Easily. And beyond that direct financial hit, there's severe reputational damage. Imagine customers unable to place orders or access services online.
Yeah, that's bad.
Then you might have legal and compliance penalties if you miss critical deadlines for financial reporting or data processing. And something often overlooked, the huge negative impact on employee morale and productivity when people just can't do their jobs.
Right, the frustration level must be immense.
It's a cascade of failures, all stemming from that one single point of vulnerability. Without a really robust high availability strategy, businesses are, quite literally, playing a very high-stakes game of chance every single day.
So it really boils down to business continuity then, preventing that absolute nightmare moment when everything just stops cold.
Precisely.
It's about building a sophisticated safety net, like a digital parachute, for when those inevitable bumps in the road happen. And that's exactly where this concept of high availability comes into play.
Exactly. To get around these potentially catastrophic downtimes and make sure business can continue smoothly, SAP engineered this high availability concept specifically for HANA. And this is, it's far more than just having a traditional backup file somewhere that you might restore after a failure. Restoring can take hours, sometimes even days.
Great, that's recovery, not availability.
Precisely. Instead, HA is about having a parallel live system that is constantly being updated, always ready, perpetually ready, really, to take over operations almost instantly.
So we're essentially talking about creating a kind of real-time identical twin of your main live system, always running in the background, ready to step in.
That's actually a great analogy. The core of this whole solution involves architecting a second parallel SAP agentness system right alongside your main, or what we call the primary agent database.
Okay, a primary and a secondary.
Correct. And the secondary system isn't just sitting there dormant. It's alive, it's listening, it's active. The absolute key enabler for this entire high availability setup is continuous data replication.
Replication, that's the magic word here.
It really is. Think of it as a constant real-time stream. Every single transaction, every tiny data change, every update that happens on the primary system flows immediately over the network to this secondary HANA database.
Wow. Immediately?
Well, near immediately, depending on the mode, which we'll get into. But the idea is constant flow. It's like having two identical notebooks, and every time you write a sentence in the first one, it magically instantly appears in the second one too.
Okay, I like that. So if the primary system does then fail, how does this constant replication actually help with the recovery? What's that transition like for the business and its users?
Right. So if the primary agent node hits an issue, goes down, the SAP application itself doesn't just sit there, twiddling its thumbs.
Right.
It automatically detects that the primary is unavailable. Then intelligently, it points to and connects with the secondary HANA system instead.
Automatically. How does that work?
This quick switch, this transition, is often managed by what's known as a clustering concept, or cluster software, more accurately.
Cluster.
Yeah, this isn't just about grouping servers together physically. It's more an underlying architectural principle where multiple systems are configured to act as a single, unified, resilient group. The cluster software is constantly monitoring the health of the primary node, like a heartbeat check.
Okay.
If it detects a failure, maybe the primary stops responding. It orchestrates this seamless failover operation. It effectively promotes the secondary node to become the new primary.
And the data, is it all there?
That's the beauty of the continuous replication.
Yeah.
Because data is constantly being sent and kept up to date on the secondary, there's virtually no data loss during this failover process.
Virtually none.
Well, depending on the specific replication mode, maybe a tiny fraction of a second in some cases. But for practical purposes, it's often considered zero data loss. All the data that was present and committed on the primary, right up to the very moment of its failure, has already been safely transferred and committed on the secondary.
That's impressive.
It is. And it ensures that business operations can resume seamlessly, often with minimal or sometimes even no noticeable interruption for the end users.
Really? So users might not even know it happened?
From a user's perspective, yeah. It might just feel like a momentary pause, maybe a slight screen flicker, or often completely unnoticeable. They can just continue their tasks right where they left off. It's truly remarkable how quickly and transparently this failover can happen when it's set up correctly.
That sounds incredibly robust, a genuine safeguard against those individual server hiccups or component failures. But our sources also mention this concept scaling beyond just a single server issue. It's not only about localized resilience, right? It protects against bigger, more catastrophic events, too, like Geographic resilience.
Absolutely, you're spot on. The high availability concept extends far beyond just protecting against a single server or host failure within one physical data center. It actually forms the backbone of comprehensive disaster recovery planning.
Okay, disaster recovery. So bigger scale problems.
Exactly. Imagine a major data center disaster. Think widespread power grid failure affecting a whole region, or a natural disaster like a flood or an earthquake hitting the facility, or even a severe cyber attack that takes an entire data center offline.
Right, things you really hope never happen.
Precisely. But if your high availability setup, your primary and secondary, only exists within that single data center, well, you'd still be in very serious trouble if that whole facility goes down. Both your systems would be affected.
Ah, okay. So you need separation.
Exactly. This is where the concept of having another HANA system, a secondary or even tertiary system, in a geographically distinct data center comes into play. This could be in another city, a different state or region, sometimes even on another continent entirely.
Across the country or even the world.
Yes. So if your primary data center goes down completely, operations can be swiftly switched over to that remote secondary data center. This ensures true global business continuity. It prevents a regional or local outage from crippling your worldwide operations.
So it's layers of protection.
It's all about building fault tolerance at multiple, ever larger levels. You start with the individual server components, then the server itself, then the network within the data center, and ultimately the entire data center infrastructure itself. The goal is to ensure your business can genuinely operate 24/7, 365, regardless of where or when an issue might strike.
Right.
The sources really highlight that avoiding these large-scale faulty tolerance issues, as they sometimes phrase it, is precisely why we extend this primary-secondary concept to such a wide geographical scope. It's a significant investment, but it's an investment in truly uninterrupted service delivery.
Okay, fascinating. We've definitely covered the why, the critical need, and the what, this parallel replicating system.
Yeah.
Now let's really unpack the how. This clearly isn't some magical on switch you just flip.
Definitely not. No magic buttons here.
So how do you actually go about setting up this incredibly resilient primary-secondary HANA system? With that real-time data replication, our sources laid out some very specific configuration steps, almost like a meticulous checklist. It seems like there's absolutely no room for error.
Indeed. It involves a very precise, very meticulous configuration process. And, crucially, before you even begin the actual step-by-step setup, there are a few critical prerequisites that absolutely must be met on both the primary and the secondary systems.
Prerequisites first. Okay.
Yes. If you miss even one of these foundational pieces, you're almost guaranteed to run into significant issues later on. It'll just stop you in your tracks.
Right. Better to get the foundation solid. What are they?
Okay, first, and this is pretty foundational, obviously, the SAP HANA database software itself must already be installed on both the planned primary and secondary hosts. You need the software installed to configure it.
Makes sense. Your blank canvas, as you said.
Exactly. Second, and this is absolutely crucial, for the logical consistency of your whole setup, both of those HMN installations must use the identical system ID, or SID,
Okay.
and the exact same instance number. Think of the SID as the overall name of your SAP landscape, and the instance number is like a unique house number for that specific HNS system within the landscape. These must match for the two systems to be recognized by SAP and the cluster as part of the same logical replication pair.
Same SID, same instance number. Got it.
However, while those logical identifiers are identical, the physical host names for the primary and secondary systems must be different. This is critical, so your network and the underlying operating system can actually tell the two distinct physical or virtual machines apart.
Okay, logical names same, physical names different.
Precisely. But now, here's probably the most critical prerequisite. This was highlighted repeatedly in our source material as a super common pitfall, one that stops many implementations dead in their tracks right at the start.
Okay, what is it?
The HANA database version. The version on both the primary and the secondary hosts must either be exactly the same, or, specifically, the secondary's version must be higher than the primary's version.
Higher, not lower.
Absolutely not lower. This isn't just a suggestion, it's a fundamental rule. It's baked into how HANA's internal data structures and replication protocols evolve between versions. If the secondary is an older version, the replication setup will simply fail.
It won't even let you try.
Nope. The system will explicitly tell you. You'll get an error message right during the registration step saying something very clear like primary must have same or greater version, or maybe phrased as secondary must have same or greater version. It's a hard stop.
Wow.
This is a really significant point because it forces you to ensure that compatibility right from the very beginning.
Yeah.
You can't just grab any old server and make it a secondary.
That's a very specific and potentially tricky version rule. Okay, so once those foundational prerequisites HANA installed, same site instance, different host names, and that crucial version rule are all meticulously met, what are the actual hands-on steps? How do you get this replication up and running and really turn on that digital safety net?
Right, so once the foundation is solid, the configuration process itself is a sequence of distinct, very dependent steps. You really have to follow them in order.
Okay, step by step. Let's hear it.
Step 1. Install HANA DB on both hosts. As we just covered, this is job number 1. Get the software installed on both your designated primary and secondary servers. And critically, as you do this, you must carefully ensure that version rule we just hammered home is followed right from the outset.
Don't forget the version rule.
Exactly. Our source material actually vividly recounts a scenario where someone tried with a lower version on the secondary, and it caused an immediate hard stop failure during the registration. Wasted a lot of time figuring that out. So version compliance first.
Got it. Step 2.
Step 2. Copy SSFS keys. Okay, once the secondary HSFS system is installed and you've confirmed its version is compliant, you move on to copying these things called Secure Storage File System keys, or SSFS keys.
SSFS keys, secure storage.
Yes, these keys are not just random files. They're absolutely essential. They handle the secure communication, the authentication, the encryption between your primary and secondary HS systems. Think of them as the database's digital passport and secret handshake.
Ah, okay. Critical security components.
Absolutely. They're typically located in a very specific, highly secured system directory, usually user Zapier, City SYS Global Securities, like a digital vault.
Okay.
And this copying is usually done using secure tools like the cp command in Linux to ensure the integrity of these sensitive files during transfer. Our sources strongly indicate this is another critical step. If it's done incorrectly or if the keys somehow get corrupted during the copy, it can lead to severe problems later.
Like what kind of problems?
Like the secondary database being completely unable to start up or failing during a later upgrade process because it can't validate its own secure components.
Okay, so handle with care. What's next?
Step 3. Restart secondary system. After you've successfully copied those vital SSFS keys over to the secondary HANA system needs to be restarted.
Just a simple restart.
It might seem small, almost trivial, but it is absolutely vital. The restart forces the secondary system to load and recognize these newly copied keys, integrating them properly into its security fabric. It also confirms that the secondary system comes up cleanly, in a stable, healthy state, now recognizing its new digital identity based on those keys.
So it's a validation step, really.
Exactly. The source material actually mentioned an experience where someone didn't restart after copying the keys and then immediately tried to upgrade and configure replication. It led to serious problems. The secondary database just wouldn't start properly, causing a lot of wasted time troubleshooting. This restart confirms the secondary is truly ready for the next phase.
Okay, keys copied, secondary restarted, and healthy. What now?
Step 4. Enable replication on primary node. With the secondary prepped and confirmed healthy, you then shift your focus back to the primary HANA system. You'll access it usually through the graphical tool SAP HA Studio, or maybe using command line tools, and you configure it to enable system replication.
Telling the primary to get ready to send data.
Precisely. This is where you explicitly tell the primary system, okay, I am going to start sending my data, my entire transaction stream, over to a secondary system. You define it as the source system for the replication process.
All right, primary is ready to broadcast. What about the secondary?
Step 5. Stop secondary system. Now here's another crucial sequencing point. Before you can formally register the secondary system to the primary, the secondary HAA database must be explicitly stopped. Shut down.
Stopped. Why stopped?
It's a non-negotiable prerequisite for the registration process to succeed. If the secondary database is running, the registration attempt will inevitably fail. You'll likely get an error saying the target database is active or online. Stopping it ensures it's in a clean, receptive state for the primary to establish that initial replication link.
Okay, primary enabled, secondary stopped. Ready for connection.
Yes. Step 6. Register secondary onto primary. With the secondary now offline, you initiate the registration process from the secondary HANA system's command line. You run a command that registers it as a designated secondary of your specific primary system.
Ah, so the secondary initiates the handshake.
Correct. And this is a really pivotal moment in the whole setup. Because during this registration step, you define those critical replication modes and operation modes, which we absolutely need to dive into next. These modes dictate precisely how the data will be replicated and how the secondary will manage it. This is where you tell the secondary, okay, you are now officially receiving data from this specific primary system, and here's exactly how you should handle it.
Got it. That sounds like where the real configuration choices happen. And the last step.
Step 7. Monitor replication. Finally, once that registration is complete and the secondary potentially starts syncing up, the process isn't actually over. It transitions into an ongoing state. It's absolutely essential to continuously monitor the replication status after registration.
Keep an eye on it.
Yes, this is an ongoing process. You need to ensure data is flowing correctly, that the systems remain in sync, and that your carefully constructed digital safety net is indeed deployed and functioning exactly as you intended. It's all about ongoing vigilance and making sure it stays healthy.
Wow. That truly is a meticulously detailed checklist. It really sounds like missing a single step or even just performing them slightly out of order could cause major headaches and lead to a significant amount of painful troubleshooting.
Oh, absolutely.
Knowing the precise order of operations and maybe more importantly the why behind each specific step seems paramount to success here.
It is. The order and the precision are absolutely paramount. These aren't just arbitrary steps thrown together, they build logically upon each other. Each step ensures the stability and the security required for the next one to work properly.
Okay, here's where, for me anyway, it gets really interesting. Because it sounds like it's not just a single way to replicate the data.
That's right.
Our sources really highlight that during that registration phase, step 6 you mentioned, you're presented with some critical choices about how this replication actually happens. It's definitely not a one-size-fits-all approach.
Right on.
Can you walk us through these critical replication modes and operation modes? They seem to fundamentally dictate the very nature of this digital safety net and, crucially, how quickly a business can actually recover if something goes wrong.
You've captured the essence of it perfectly. These modes are absolutely foundational to how SAP HANA High Availability functions in practice. And choosing the right combination, well, it dictates that delicate balance. You're constantly balancing between paramount data consistency, optimal system performance, and your desired recovery time objectives, RTO, in the event of a primary system failure.
RTO, recovery time objective, how fast you get back online.
Exactly. And also RPO, recovery point objective, how much data you might potentially lose. Understanding these modes isn't just a technical exercise for the IT folks. It's key to choosing the right strategic approach for your business's specific needs. You have to consider its risk tolerance, maybe regulatory requirements for data loss.
Makes sense. So let's break them down. Replication modes first.
Right. Let's start with the replication modes. There are 3 primary types, and each one has really distinct implications for data safety and how your systems are going to perform. First up is synchronous, often just called sync.
Synchronous.
Okay, mechanism. With sync, when the primary HNS system processes a transaction, say, saving a sales order, and sends it over to the secondary, the primary does not proceed with its next transaction until it receives a definitive acknowledgement back from the secondary.
It waits.
It waits. And crucially, that acknowledgement is sent back only after the data has been securely written to the secondary's persistence layer. That means it's physically committed to disk storage on the secondary system. Think of it like sending a registered mail package. The sender waits until they get that signed return receipt before they move on to their next task.
Okay, very deliberate. What's the implication of that waiting?
Implication. The huge benefit here is the absolute guarantee of zero data loss, RPO 0. Because the primary makes sure the secondary has safely stored the data to disk before it commits its own transaction locally. If the primary suddenly crashes, you are 100% certain that every single transaction that was successfully completed on the primary is also safely stored on the secondary's disk. This offers the highest possible level of data consistency.
The zero data loss, that sounds ideal.
It is ideal for scenarios where losing even a single transaction is completely unacceptable. Think financial trading systems, critical payment processing.
Right. But there's always a trade-off, isn't there?
Trade-off, yes there is. This ironclad robustness comes with a potential performance cost. It can introduce latency, a slight delay, into the transactions happening on the primary system. If the network connection between the primary and secondary is slow, or if the secondary system itself is under heavy load or experiencing performance issues, the primary will be blocked, just waiting for that acknowledgement.
So the primary slows down?
Potentially, yes. This latency can impact the overall throughput and performance of the primary system, especially in extremely high-volume transaction environments. But for many critical systems, that guarantee of zero data loss is considered well worth the potential performance hit. Next, we have synchronous in-memory, usually shortened to SyncMem
SyncMem. Okay, sounds similar but different.
mechanism. It is similar to sync. It's actually a highly optimized variation. The primary still waits for an acknowledgement from the secondary before proceeding.
Still waits.
But in this case, the acknowledgement from the secondary is sent back as soon as the data reaches the main memory level on the secondary. It does not wait for the data to actually be written to the physical disk on the secondary side.
Ah, okay, so it confirms once it's in RAM, not on disk.
Exactly. Implication. Because it skips that disk wait time on the secondary, SyncMem is notably faster than the full synchronous mode. It offers much better primary system performance while still providing a very, very high degree of consistency and effectively minimal data loss potential.
Minimal, not zero.
Technically, there's a tiny theoretical window. If both the primary and the secondary were to crash simultaneously after the data hit the secondary's memory but before it was flushed to the secondary's disk, you could lose that last transaction. But the data is securely in the secondary's memory.
Right. The chances of that double failure seem incredibly low.
Statistically, extremely low, which is why SyncMem is often considered sufficient for many mission-critical use cases. It strikes an excellent balance between high performance on the primary and very strong data protection. It's a very popular choice. And the third mode is asynchronous, or async.
Asynchronous, so not waiting.
Mechanism, exactly. This is where the behavior changes quite significantly. With async, the primary sends the data over to the secondary, but does not wait for any acknowledgement at all before proceeding with its next transaction.
Just fires it off.
Pretty much. It continues processing its own transactions, sending more data packets, regardless of whether the secondary has actually received or processed the previous ones. It's truly a fire-and-forget approach from the primary's perspective. Think of it like sending a regular email. You hit send and you move on. You don't sit there waiting for a reply confirmation.
Okay, that sounds much faster for the primary.
Implication, absolutely. Async offers the highest performance for the primary system among all the replication modes, because the primary is never blocked or slowed down by the secondary. This makes it ideal for scenarios where you have long geographical distances between your data centers or environments with inherently high network latency. In those cases, synchronous modes would likely introduce unacceptable delays and significantly degrade the primary system's performance.
Makes sense for long distance, but the trade-off here must be data loss potential.
Trade-off, yes, that's the crucial trade-off. There is a potential for some data loss during a failover event. If the primary crashes suddenly before the secondary has received or processed all the transactions that were in transit over the network, those last few transactions might be lost forever.
How much data could be lost?
This is quantified by the recovery point objective, the RPO we mentioned. It's the maximum acceptable amount of data, usually measured in time, that your business is willing to lose in a disaster. With async, your RPO is typically non-zero. It might be measured in seconds, maybe even minutes, depending on network conditions and load.
Okay, so not zero data loss guaranteed.
Correct. Common use case. Because of this potential for minimal data loss, asynchronous replication is primarily used for disaster recovery DR scenarios, especially when the primary and secondary sites are geographically far apart. The significant performance gain over those long distances is often deemed worth the minimal acceptable risk of losing a tiny bit of data.
Okay, that clarifies the three replication modes. Sync for zero loss but potential latency, SyncMem for great balance, and async for best performance over distance but with a small RPO. Now, what about the operation modes? You mentioned those two.
Right. The operation modes dictate how the replicated data is actually managed and applied on the secondary system. These primarily impact your recovery time objective, RTO. Remember, that's how quickly you can actually get the system back online and usable after a primary failure. There are two main ones here. First is delta data shipping.
Delta data shipping, okay.
This mode involves the continuous log shipping, basically sending the transaction logs from the primary to the secondary as they are generated. But additionally, periodically, the default is usually every 10 minutes, but it's configurable separate delta data shipping occurs. This is where snapshots of changed data blocks, not just logs, are transferred asynchronously from the primary to the secondary.
Logs continuously, data snapshots periodically. Why both?
Implication. The secondary system receives all these logs and the periodic data snapshots. However, the logs themselves are typically not fully committed or replayed onto the secondary database until an actual takeover event occurs. They're just stored, accumulating. The purpose of those periodic data snapshots is mainly to help shorten the log replay time during a takeover.
How does it shorten the time?
Well, if you only had logs going back hours or days, replaying all of them from the last full backup could take a very long time during a stressful recovery. These delta snapshots provide more recent starting points for the log replay process, meaning you only have to replay logs since the last snapshot, making the recovery faster. So the secondary is essentially building up a historical record of changes, but it's not actively applying them live in real time. It's more of a warm standby. The second operation mode is log replay.
Log replay sounds more active.
Mechanism. It is. This mode focuses on the continuous replication and the immediate replay of those redo logs. Redo logs are the detailed chronological record of every single change, every transaction happening on the primary database. In log replay mode, as soon as the secondary system receives these logs over the network, it starts applying them, updating its own memory structures and its persistence layer disk.
So it's actively processing the changes as they arrive?
Exactly. Implication. This ensures that the secondary system's data is an almost exact, up-to-the-minute, actively processed reflection of the primary database. The critical benefit of log replay is that it enables immediate failover. This provides a very, very low RTO.
Because it's already caught up.
Precisely. Because the secondary is constantly replaying the logs and actively updating its state, it's essentially a hot standby system. It's ready for an instant takeover with minimal delay needed for recovering actions. This is often crucial for those truly mission-critical applications where every single second of downtime costs the company significant money or reputation.
That makes a lot of sense, especially understanding how log replay directly impacts that recovery time objective, the RTO. So thinking about practical application, when would you typically combine these? What are the common pairings for, say, a production environment where maximum uptime and zero data loss are key versus maybe a disaster recovery setup where geographical distance is the main challenge? Excellent question, because the combination you choose is absolutely key to fulfilling specific business requirements. It's not just picking one from each list, it's about the right pair. So for a production environment, meaning your primary talking to its immediate secondary, often in the same data center or a nearby one, purely for high availability.
To keep the main protection layer.
Yes. Here, maximum data consistency, RPO 0, and an immediate failover, very low RTO, are usually paramount. You can't afford to lose data, and you need it back online now. So the typical most common combination is log replay operation mode, paired with either synchronous or asynchronous in-memory replication mode.
Log replay with sync or sync mem.
Exactly. This pairing ensures that every transaction is confirmed as received on the secondary, either in memory or on disk, and it's continuously being replayed there. This means the secondary is always a hot, fully up-to-date standby, ready for an instant switchover with virtually zero data loss and minimal interruption. This is really your gold standard for critical, high transaction volume applications. Think core financial systems, mission-critical ERP modules.
Okay, that's clear for HA. What about the disaster recovery DR scenario, where the secondary site is far away?
Right. In a DR setup, especially when your primary and secondary sites are geographically distant, maybe hundreds or thousands of miles apart, network latency becomes a significant, unavoidable factor.
The speed of light limit, basically?
Yes, plus network hops and congestion. In this case, the common combination is usually log replay operation mode paired with asynchronous replication mode.
Log replay with async. Why that combo?
Here, you're making a very calculated trade-off. You accept the potential for minimal data loss. Your RPO might be a few seconds, maybe a minute, because the performance gain you get from asynchronous replication over those long distances is crucial. It keeps the secondary as up-to-date as possible without blocking and slowing down your primary production system during normal operations.
So prioritize primary performance over absolute zero data loss in DR.
Often, yes. And you still use log replay as the operation mode because you still want the secondary to be applying those logs as they arrive. This ensures it's ready for a quick takeover if the primary site is completely lost. The takeover might not be instantaneous, like with sync mem, because there might be a small log backlog to catch up due to the asynchronous nature, but it'll still be relatively fast. This combination is ideal for systems that are critical but can tolerate a very small window of potential data loss if it means avoiding a major performance hit on the primary site day in, day out.
Okay.
These choices, sync versus sync mem versus async, delta data shipping versus log replay, they are fundamental architectural decisions. And honestly, a business leader, not just an IT expert, really needs to understand the implications. You're choosing between absolute zero data loss potentially impacting performance or optimizing performance and distance resilience while accepting a tiny defined risk. Your critical business requirements, things like regulatory compliance, the financial impact of downtime per hour, customer expectations, they should ultimately drive which of these powerful combinations you choose for HA and for DR.
Right. Any complex technical setup like this is rarely smooth sailing, is it? Theory is one thing, but actually doing it, the practical implementation, always seems to throw curveballs.
Oh, inevitably. Murphy's Law loves IT projects.
Exactly. And our sources offered some really specific practical insights into the kinds of challenges and troubleshooting people run into. Lessons learned straight from the trenches, it sounds like.
Yes, very much so.
What are some of the most common pitfalls people encounter when setting up Hansia? And what did we learn from the sources about actually overcoming them? This feels like the really valuable, hard-won knowledge part.
It absolutely is. This is where the practical experience really comes into play, and the source material provides invaluable lessons, often gleaned from real-world debugging sessions that probably involved a lot of head-scratching.
I can imagine.
These are critical aha moments for anyone implementing SAP HA and HA. Because honestly, these common issues often cause significant delays, frustrating hours, and a lot of wasted effort if you're not aware of them beforehand. Probably the most emphasized learning, almost like a central theme running through the troubleshooting narratives in the sources, was that version mismatch rule we talked about in the prerequisites.
Back to the version rule again. It sounds really important.
It is critically important, the issue. The source explicitly details scenarios where teams tried to register a secondary system that had an older, lower HR version than the primary. The system just will not allow this. Full stop.
It blocks it completely.
Yes, it flat out refuses the registration command.
Yeah.
You get an unambiguous error message right there on the screen stating something very clear like primary must have same or greater version or secondary must have same or greater version. It's a hard stop, not some warning you can click past. This isn't some subtle technical glitch. It's a fundamental incompatibility based on how HANA's internal structures change between versions. Imagine trying to plug a very old peripheral into a brand new computer. The protocols just don't match.
Okay, so the solution is obvious but critical.
The solution. Yes, the absolute requirement, as the source discovered through trial and error that caused them significant time and effort, is that the secondary HANA system must be updated to at least the same version as the primary, or preferably even a higher version, before you even attempt to enable replication. There's simply no workaround.
Plan your versions carefully from the start.
Exactly. This highlights that you can't just pick any spare hand installation you have lying around and designate it as your secondary. It has to be rigorously compatible from a version perspective. This simple version check is such a common trap, often overlooked in the rush to get the systems connected.
Okay, version mismatch is public enemy number one. What else trips people up?
Another significant area of challenge revolves around those SSFS key issues. Remember the secure storage file system keys we talked about copying? The database's digital identity.
Right, the secure key.
The issue. Getting these keys copied incorrectly or having them corrupted during the transfer, or maybe even having leftover keys from a previous failed attempt, all of this can lead to severe problems down the line. The source specifically mentioned encountering errors like cannot create the secure storage during startup, or weird error while upgrading messages that were eventually traced back directly to issues with these keys.
So if the keys are wrong, the secondary can't even function properly.
Correct. If these keys are not copied correctly and validated, the secondary database might not even be able to start up cleanly. Or it might start but then fail during a subsequent upgrade process because it can't verify its own secure components or communicate securely with the primary or other parts of the system. It really tells us these keys are absolutely fundamental to the secondary system's ability to operate securely and integrate correctly into the replication partnership. It's like having a house where the master key for the security system is either missing, bent, or the wrong key entirely. Nothing security related is going to work right.
Okay, so what's the fix? Be super careful with the copy.
The solution. Yes, meticulous care is needed. You must ensure these keys are copied correctly using appropriate secure commands like STP. You need to verify file permissions and ownership after the copy. And crucially, after copying, you must perform that restart of the secondary system and then verify that it starts successfully and shows a healthy status before you proceed with enabling and registering replication.
That restart validation again.
Yes, it confirms the keys are loaded and functional. If issues still persist after you've been careful, a completely clean reinstallation of the secondary, making absolutely certain you manage these keys properly from the very start, might be the only reliable way forward. The source material showed how lingering bad key files from a previously failed installation could absolutely sabotage subsequent setup attempts.
Which leads nicely into another point you mentioned, cleanup.
Exactly. This leads directly to the importance of cleanup for failed installations.
So don't just try again on top of a mess.
Precisely. The issue, if a previous HANA installation or maybe a replication setup attempt failed, it's often not sufficient to just try running the installer or the configuration commands again over the top of the old attempt. Residual files, old configuration settings, and especially those old, potentially problematic SSFS keys can linger on the system file system.
Digital ghosts, you called them.
Yes. These digital ghosts can cause new installation attempts or replication setups to fail in completely unpredictable and often very confusing ways. The source explicitly noted needing to perform a full cleanup because previous failures had left behind conflicting remnants. You might get errors complaining about existing directories or files blocking the new install, or strange configuration conflicts.
So scorched earth policy before trying again.
The solution? Pretty much. Performing a full, meticulous cleanup before attempting a fresh start is absolutely crucial after a failure. This usually means not just using the standard uninstall routine provided by SAP for HANA, but also manually checking critical system directories and removing any leftover folders or files related to the previous attempt. The source mentioned commands like arm-rf usrs-sid or similar, obviously used with extreme care, for this purpose.
Be careful with arm-rf.
Absolutely. But the point is, this ensures you're starting from a truly pristine, clean environment, free from any conflicting remnants of past attempts. It gives your new installation the best possible chance of succeeding without weird interference.
Okay, versions, keys, cleanup. Any other major hurdles?
One more that the source has really underscored: the crucial need for precise sequencing of start-stop commands.
The order matters a lot.
A huge amount.
Yeah.
Issue. The entire setup process, as we walk through the steps, requires very specific start and stop sequences for the HANA databases involved. For example, remembering that the secondary database must be stopped just before you register it to the primary. If it's left running, the registration command will fail, usually with a simple message saying the target database is active or online.
Right.
Conversely, after you copy those SSFS keys, the secondary should be started to confirm its health and show the proper loading of those keys before you move on to enabling replication on the primary and then trying to register.
Got it. Sequence is key.
The source material demonstrated how deviating from this precise order, for example, someone immediately attempting an upgrade right after copying keys without doing that intermediate restart and health check led directly to database startup failures and a lot of unnecessary debugging time. It's really like following a complex recipe. The ingredients must be added and steps performed in a very specific order for the dish to come out right.
You can't just wing it.
The implication, exactly. This isn't just about typing commands in the right order. It's about understanding the internal state transitions that the systems need to go through. Deviating from these required sequences can lead to confusing system errors, database startup failures, or simply failed replication setups, turning what should be a relatively straightforward, if detailed, process into a lengthy and incredibly frustrating troubleshooting exercise. It's a real testament to why detailed runbooks, checklists, and meticulous execution are so vital in these complex IT environments.
So, bottom line, it's not just about knowing what to do, but critically knowing when and how to do it. Understanding that order of operations really, really matters. These practical lessons, often learned the hard way in real-world implementations as the sources show, are truly invaluable for anyone planning to tackle a complex solution like SAP HANA High Availability.
Absolutely.
It really highlights that practical implementation aspect we wanted to focus on in this deep dive. It's where the rubber meets the road.
Precisely. Every single issue encountered in a real-world setup, every error message, becomes a valuable learning point. It reinforces exactly why these steps and rules are defined so strictly and why that meticulous attention to detail is completely non-negotiable for success.
Okay, so let's say you've navigated all those steps, dodged the pitfalls, your prerequisites were perfect, you carefully selected your replication and operation modes. The setup itself is complete.
Right, you built a safety net. Exactly.
Yeah.
But the job isn't quite done. The final critical step, and really, it's an ongoing one, is validating that the replication is actually working exactly as you intended it to. You can't just set it and forget it. You need proactive, ongoing vigilance.
Makes sense. You need to know the net is actually holding. How do you verify it's doing what it's supposed to do? What specific tools or key indicators should you be looking for to ensure that digital safety net is truly deployed, active, and healthy?
You'll primarily rely on robust monitoring tools. The main one in the SAP ecosystem is usually SAP HANA Studio. It acts as a central command center, giving you a comprehensive overview of your entire HANA landscape, including replication status.
HANA Studio.
Within HANA Studio, you'll find dedicated sections, specific views, designed purely for monitoring system replication status. These are your main windows into the health of the connection.
What should you be looking for in those views?
Well, the key status indicators you'll be looking for typically progress through a logical sequence, especially right after the initial setup. Initially, right after you complete the registration, you might see statuses like initializing, or maybe syncing, or even full replica is happening.
Meaning it's copying the bulk data.
Exactly.
This indicates that the initial synchronization of the entire database content from the primary over to the secondary is currently in progress. This initial sync can take a significant amount of time, could be minutes for a small system, could be many hours, even days for a huge multi-terabyte database, depending on its size and your network bandwidth. It's that big initial bulk transfer of all existing data.
Okay, so initializing is normal at first. What's the goal state?
The ultimate goal, your desired end state, the everything is healthy indicator, is to see all the relevant HANA services and components showing a status of active in sync.
Active in sync. That's the magic phrase. That's the one you want to see. When you see active in sync across all the various components of your HANA system, like the index server, the name server, compilation service, etc., it provides strong confirmation. It tells you that data is continuously flowing correctly from the primary to the secondary in real time or near real time, and that both systems are fully synchronized and ready for a potential failover if needed.
Okay, look for active in sync. Is that enough? Or are there deeper metrics to watch?
That status is crucial. But beyond just that overall active in sync status, you should also ideally be continuously monitoring specific replication metrics. These give you deeper insights into the actual health and performance of your replication link. Things like the replication count, maybe logs shipped or bytes transferred. This tells you exactly how many transactions or changes have been successfully replicated. Seeing a steady, continuously increasing count is a very good sign. Also, the log position. This indicates how far along in the transaction log stream the secondary system is compared to the primary. If you start seeing a significant and growing lag here, that could signal a performance bottleneck on the secondary system, or maybe a network issue slowing things down. And the timestamp of the last successful replication or log shipment. This helps you track the recency of the data on the secondary and quickly identify any unexpected delays or stalls in replication.
So these metrics help you spot problems early.
Exactly. These metrics are crucial for proactive monitoring. They allow you to catch and address any potential issues like network congestion or a slow secondary early on before they become critical problems that might impact your ability to fail over successfully.
Right, so you're monitoring the technical status and metrics. But beyond just looking at the screens and numbers in HANA Studio, is there a more practical, maybe hands-on way to really confirm that data is flowing properly from the primary to the secondary, something that gives you that concrete, undeniable proof that it's working end-to-end?
Absolutely. And it's a really good practice to do this, especially initially and maybe periodically afterwards. A very practical and confidence-inspiring way to confirm replication is working is by performing a simple yet highly effective data verification test.
A test transaction.
Essentially, yes. This involves creating some piece of new data on the primary system. For example, you could create a new test user account, or maybe make a new entry in a configuration table, or perform a small, completely non-critical test transaction if your application allows.
Something simple and safe.
Exactly. Then you immediately connect to this secondary system and verify that this new piece of data has automatically appeared there, usually within seconds if you're using log replay.
Ah, okay. See it appear on the other side.
Precisely. The source material we looked at specifically mentions a scenario just like this, where a tester created a new user. They even gave the example username Raju Ravi Ravi 1 on the primary system, and confirmed it was instantly visible when they queried the user list on the secondary system.
Instant proof.
Yes. This kind of hands-on test provides concrete, undeniable proof that all data, including brand new entries created after the initial sync, is being replicated continuously and successfully. It confirms that your high availability setup is truly providing that digital safety net you so meticulously configured. It's really the ultimate confirmation that your twin system is indeed perfectly mirroring your primary, ready to take over.
So when you boil it all down, at the end of the day, it's truly about confidence, isn't it?
It really is.
Confidence that your critical business data is safe. Confidence that your business can keep running, keep operating, no matter what unexpected curveball gets thrown its way by technology or circumstance. It's truly about building a profound layer of resilience right into the very core of a company's operations.
Well said. That's the ultimate payoff for all that careful configuration and monitoring. Peace of mind. Hashtag outro.
Wow, what an insightful deep dive that was. We have really navigated through the intricate, sometimes daunting complexities of SAP HANA High Availability and Replication today.
We certainly covered a lot of ground.
From understanding why it's become an absolute essential for basic business continuity and robust disaster recovery in our modern, always-on digital world,
The fundamental need.
to walking through the very precise, step-by-step, how the configuration process required to set it up correctly.
Including all those crucial prerequisites and potential pitfalls.
Exactly, and grasping the nuanced but critical differences between the various replication and operation modes, understanding those trade-offs between data loss, performance, and recovery time.
Sync mem, async, delta data, log replay, lots to consider there.
We even explored those common pitfalls, the version mismatches, the SSFS key problems, the importance of cleanup, the critical start-stop sequences, and gleaned those crucial learnings from practical, real-world implementations. Realizing that often the smallest missed detail, like that version mismatch or a skipped restart, can completely halt the entire process.
It truly highlights that technical knowledge is most valuable when it's deeply understood and meticulously applied in practice. Every issue encountered during a real setup, just like our source material clearly demonstrated, becomes a really valuable lesson learned. It reinforces the absolute importance of meticulous attention to every detail and strict adherence to those established best practices in system architecture.
Yeah.
These systems are specifically designed for resilience, right? And building them effectively demands an equally resilient, precise, and careful approach from the people implementing them.
You know, this deep dive has really revealed the incredible, often invisible engineering that works tirelessly behind the scenes, just keeping our digital world running so seamlessly most of the time.
It's easy to forget what goes on underneath.
It really makes you wonder, how many other hidden systems, completely invisible to the everyday user like you and me, are working just as tirelessly around the clock to ensure the services we rely on every single day, banking, shopping, communication, are always there, always available?
That's a fascinating thought. The hidden infrastructure.
What other layers of unseen resilience are built into this vast digital fabric that surrounds us, constantly preventing unseen disasters, ensuring our online world just keeps going despite all the potential points of failure? Something to definitely mull over until our next deep dive.